day, students. Today I will be discussing with you our third topic, which is motion and machinery. Maybe right now you are already wondering how mechanisms work, how to achieve a certain motion, how does a particular mechanism achieve such kind of output. That will be answered in this topic. By the end of this discussion, you should be able to define the following concepts: linkages, joints, links, kinematic diagrams, degrees of freedom, mechanism and structure, Gruebler paradoxes, intermittent motion, inversion, and the Grashof condition. Analyze the mobility and the Grashof condition of linkages. Build an actual linkage to investigate the concepts of degrees of freedom, mechanism and structure, inversions, and Grashof condition. Discuss the importance of the concept of degrees of freedom and Grashof condition in the analysis and synthesis of mechanism. This will be the outline of my discussion. Let us start with the types of motion. As I mentioned earlier, the primary objective for machines or mechanism is to produce a certain kind of motion. There are different types of motions. It can be pure rotation, wherein the body possesses one point called the center of rotation that has no motion with respect to the stationary frame of reference. All the other points on the body describe arcs about its center. A reference line drawn to the body through the center changes only in its angular orientation. An example of a pure rotation is, for example, a pure rotation of a flywheel. Another type of motion is the pure translation. Here, all points on the body describe parallel, which can either be curvilinear or rectilinear paths. A reference line drawn on the body changes its linear position but does not change its angular orientation. An example of this is, say, for example, when you walk. All points in your body change as its distance with respect to the original position, but each of the position is parallel with respect to the path. Then we have complex motion. In a complex motion, it is a combination of simultaneous rotation and translation. Any reference line drawn on the body will change both its linear position as well as angular orientation. So you can see here, points on the body will travel non-parallel paths, and there will be at every instant a center of rotation which will continuously change location. An example for this is the wheel of your bicycle, for example. So as you move the bicycle, the wheel rotates, and at the same in a center of rotation, but at the same time it's also having its translation. This is how pure rotation looks like. So there is a center of rotation, and the other points in that object, for example, is moving and changing its angular orientation with respect to the center of rotation. Then we have the pure translation, wherein all members or all points is moving parallel in the center of the path. And then a rolling motion, which is a combination of both the pure rotation and pure translation. So it's important to define that type of motion that is required for a mechanism. Say, for example, you are designing a windshield. So in the windshield, we want to wipe, say, for example, the front of the windows, say, for example. So when you desire to create that kind of motion, wiping motion, then you have to design also the inputs so that you can achieve the desired output or the desired motion. So how do we design that? So let us talk about linkages. In linkages, we'll talk about two important concepts, the concept of links and the concept of joints. So let us first define linkage. Linkage is the basic building blocks of all mechanisms. The common forms of mechanisms such as cams, gears, belts, and chains are variations on a common theme of linkages. So they are composed of linkages. Linkages are made up of links and joints. So what is a link? So links are assumed to be rigid, wherein forces are neglected. So when we design here the links, we neglect the effect of forces in the link. So that's why we consider it as rigid. So rigid here does not change its shape, does not bend because we neglect the effects of forces. So that's also the simplicity in kinematics. Links have nodes for attachment of the different links. Can be any shape. The order of the link is the number of nodes. Say for example, the binary link has two nodes, ternary link has 3 nodes, quaternary link has 4 nodes. So here in this figure, we can see the binary link with 2 nodes, ternary link, and the quaternary link. So in the nodes, this is where you connect the other links. So here, let us define the links that we can encounter later on. We have the crank. A crank is a link that makes a complete revolution and is pivoted to the ground. Rocker, on the other hand, is a link that has oscillatory or back and forth rotation and is pivoted to the ground. Then we have the coupler or the connecting rod, a link that has a complex motion and is not pivoted to the ground. The ground is any link or links that are fixed, which is meaning it's non-moving with respect to the reference frame. So to illustrate the difference, so you can see here, we have the link here at the bottom is called the ground. Then the link that will rotate is called the crank. And then we have the rocker, the one that will oscillate. Both the crank and the rocker are pivoted to the ground. The coupler, on the other hand, is not pivoted to the ground. So this one, the one at the top link is the coupler. So let us try to see how they rotate. So you can see here that the link that is ground does not move at all. The link that is the crank, it rotates. Then we have the rocker, it oscillates. Then we have the coupler, it has a complex motion, as you can see here. So in this animation, you can also see the path of the crank and the rocker. So you can see that as the crank rotates, the rocker oscillates because of their connection. Aside from links, it's also important to define joints. The joints are also called kinematic pairs. The joints allow degrees of freedom between links. So when we say it allows degrees of freedom, it means it allows mobility between links. There are classification of joints. It can be classified by the type of contact between the elements. It can be line, point, or surface. It can be classified as by the number of degrees of freedom allowed at the joint, and by the type of physical closure of the joint, which can either be force or form close, and by the number of links, which is also known as the order of the joints. Based on the type of contact, it can be classified as lower pair or higher pair. Lower pair has joints with surface contact, so meaning when the two joints are connected in such a way that their surface is in contact with each other, it's called lower pair. Joints with point or line contact are considered as higher pair. Then we have by the number of degrees of freedom allowed at the joint, meaning the mobility that is allowed at the joint, it can be considered as full joints. Joints that have 1 degree of freedom is considered as full joint. An example is the screw and the nut. So for the screw and the nut, you can see later on that there is only one mobility for the screw and the nut, which is it will advance by rotating it. So it's considered as a full joint. It's considered as half joints when it has 2 degrees of freedom. They are also called the roll and slide joint. So when you have a joint that has this roll and slide, then it's considered as a half joint because it has 2 degrees of freedom, meaning it can roll, then it can slide also. And then we have also 3 degrees of freedom wherein it can move in 3 ways, such as the ball and socket joint, joystick, or the ball joint. By the type of physical closure of the joint, we can classify it as force close. So for the force close, it requires some external force to keep it together or close. So for example, it requires a spring so that the two components will remain attached to each other. Then we have a form close wherein they are kept together or closed by its geometry. Example is a pin in a hole. And then we have by the number of links. So the number of links, we can classify it as the number of links joined minus 1. So the degrees of freedom, if we have the number of links, is just the number of links minus 1. So to illustrate it further, so you can see here in this table the 6 lower pairs. So they are the revolute symbol with a symbol R, prismatic P, helical H, cylindric C, spherical S, and planar S. So you can see there that the degrees of freedom for a revolute, prismatic, and helical pairs are 1. The degrees of freedom for cylindric is 2. For spherical, it's 3, as well as for planar. The constraints there can also be seen. You can see based on the symbol. It can either be revolute or prismatic. So you can see here also the schematic diagram for the revolute joint, prismatic joint, helical joint, cylindric joint, spherical joint, and the planar joint. So let us try to examine them further. So you can see here the 3 of the 6 lower pairs. So we have for the revolute joint or the revolute R joint, you can see here that the end points are actually fixed. So that's why it can only move, it can only rotate along its axis. It is not allowed to slide to the right, or to the left. It can only rotate with respect to the axis. So it has the 1 degrees of freedom. So that's the revolute. For the prismatic, so here for the prismatic, it doesn't have an axis of rotation. It is only allowed to slide to the left or to the right. So that's why it has only 1 mobility or 1 degrees of freedom. For the helical joint, because of the design here of the nut, the bolt and the nut connection, you can see that it cannot slide to the left or to the right. It will only rotate also. That's why it has 1 degree of freedom. Also, we can classify the joints as either form close or force close. But here at point B, so what we see here are actually full joints. So we learned that full joints have 1 degrees of freedom. So these are full joints which are also lower pair. So they are full joints because they have 1 degrees of freedom. So you can see that for this rotating full pin joint, it is only allowed to rotate. So that's why it has 1 degrees of freedom. On the other hand, for this translating full slider joint, it is only allowed to slide. So that's why it has 1 degree of freedom. The contact between the two is considered as lower pair because there is a surface contact between the joints. So for the rotating full pin, it is considered as a form close because it requires because it does not require a force at all, so that they are connected. Also for this translating full slider here, they are considered as a form close because there's no force required to maintain the connection between the slider and the slat. So that is full joints, and we have here at the bottom, we have at C, this is a roll slide joints. So we learned that a roll slide joint has 2 degrees of freedom, so that's why it's called half joint. So here we have higher pairs because the contact between the two joint is actually a point contact. So there's a point contact between the link 1 and link 2. Same also with the slat here, and the link, the pin and the slat is also has a point contact, so that it's considered a higher pair. So for the link against plane, it's considered as a force close because it requires force for them to stay connected. So if you remove the force, they will no longer be connected. So the degrees of freedom is 2 because it is allowed to rotate, and it's also allowed to translate. And for the pin and the slat, it is considered as form close because they are already connected using without any force. They are still connected here because of the slat, because of the geometry of the joints. Also, this is considered as 2 degrees of freedom because the link here can rotate, and then the joint here can translate. Then we have here the cylindric joint, spherical joint, and the planar joint. For the cylindric joint, you can see here that when we remove the constraint at the end, so if we have constraint at the end, it's considered as a revolute. But when you remove that, you can see here that it can rotate on its axis, and it can also translate. So that's why it has 2 degrees of freedom. For the spherical joint, just like the ball and socket, it has 3 degrees of freedom because you can rotate it to the left, to the right. You can see here at 3 directions. So that's why it's a spherical joint. It has 3 degrees of freedom. Same also with the planar joint here. You can actually move that in the X direction, the Y direction, or rotate it. So that's why it has 3 degrees of freedom. And then for the order of the joint is 1 less than the number of joints linked. So you can see here that there are 2 links, so that's why the order of the joint here is 1. So it's 1 degrees of freedom. And then we have for the second one, there are 3 links. So the degrees of freedom is 3 minus 2, so meaning 3 minus 1, so that's why it has 2 degrees of freedom. So therefore, the order of the joint, which is also the degrees of freedom, is 1 less than the number of links joined. And then we have here planar, pure roll, pure slide, or roll slide joint. So it can either have 1 degrees of freedom or 2 degrees of freedom, and it's considered a higher pair because there is a point or line contact between the two. It can roll, it can slide, or it can do both depending on the presence of friction. So that's why it's actually complex kind of motion. So those are the linkages. It's important to establish your vocabulary as well as your understanding about the joints, the links, and how to count the degrees of freedom of the joints. Because later on, it will help us also to determine the degrees of freedom of the whole mechanism. For the kinematic, the third subtopic is the kinematic diagrams. So as you can see, in the previous presentation, I have shown you some diagrams. So some of them are called kinematic diagrams. Kinematic diagrams, in analyzing the kinematics of mechanisms, it requires that we draw clear, simple, schematic kinematic diagrams of the links and joints of which they are made. Joints can allow rotation. It can also allow translation or both between the links joint, as you can see in the different lower pairs. So there are times that the joint can allow rotation, translation, or both between the links being joined. The possible joint motions must be clear and obvious in the kinematic diagram. So you can see here the schematic notation for kinematic diagrams. For the binary link, ternary link, quaternary link, grounded half joint, you have the moving rotating joint, grounded rotating joint, we have moving translating joint, grounded translating joint. So for the grounded, you can see that there are lines here, so that means it's grounded. So when you see a circle, it's just a joint. When you see a line and two joint, then it's considered a binary link. You can see here a moving translating joint, meaning it will just translate here. And then we have grounded translating joint. Then we have moving half joint. So this is a moving half joint because there is a surface, there is a point contact between this. This is considered as a higher pair also, and it's considered as a half joint. So for example, you can see here for this mechanism, when you connect them together, you can see the different parts, the grounded rotating joint, you can see the different links and the parts that are grounded and how they are connected together. So for example, this weight training mechanism. So for a weight training mechanism, what we usually do is we put a weight in the link 6, and then as an exercise machine, we put our legs, we push the link 2 here, and then so that we can exercise. So the equivalent kinematic diagram of this weight training mechanism is shown on the left photo. So you can see here that the ground link here is the link 1. So all the ground are actually considered as link 1. So you can see here they are all L1. So all the ground are considered link 1 because basically everything will just be put in the grounded. Rockers here are the links 2, 4, and 6. We have the couplers are the link 3 and 5. We have the input force F is applied to link 3 by pushing it with your legs. And then we have the output resistance weight acts on the link 6, meaning you have to overcome that weight so that as you push the link 3 with the force from your legs. So that is just an example of how we can draw the kinematic diagram of a mechanism. Say for example, the weight training mechanism. So now that we know the kinematic diagrams, let us try to examine the degrees of freedom. So what do we mean by degrees of freedom? It is also called mobility or symbolized by M. It is a number of independent coordinates needed to define the position of a body. Say for example, you have a pencil in a flat surface. So how many degrees of freedom does a pencil have in a flat surface? So as you can observe, to determine the position of the pencil, you have to establish its distance from the x-axis, its distance from the y-axis, as well as its rotation. So that's why the degrees of freedom is actually 3. So meaning there are 3 mobility that you have to consider so that you can establish the position of the pencil. So basically that's what degree of freedom means. So these are independent coordinates that are needed to define the position of the body. It is also defined as the number of inputs that need to be provided in order to create a predictable output. So just like what we said a while ago, say for example, your output is a rotation or a translation or a rolling slide, then you have to determine the input needed so that you can produce the predictable output. These are also defined as the number of independent coordinates required to define its position, just like what I stated a while ago. And to determine the overall degrees of freedom or mobility of any mechanism, so that we are referring here as the overall, we must account for the number of links and joints and for the interactions among them. So that's why we have to be familiar with the links and the joints. Let us look at this, for example. We have here two unconnected links. So for these two unconnected links, their motion is not restrained because each of these can actually, they are free to rotate, to move up or down or left or right. So if you are going to count the total of mobility for these two unconnected links, we can see that there are 3 degrees of freedom for the link 1 and then another 3 for the link number 2. So for these unconnected links, the total degrees of freedom is 6. Now that you connected, when we connect the 2 links using a full joint, you can see here that each of the link are free to rotate. So that is equivalent to 2 degrees of freedom. And the connection between them can move up or down or left or right. So the total degrees of freedom for these connected links is now 4. And finally, when you connect them by using a roll slide half joint, you can see that the first link and the second link can rotate. So we have 2 degrees of freedom plus the first link can move to the right or to the left, up or down. So that's another 2 degrees of freedom. So that is 4. And then for the second link, it can only move to the left or to the right. So that is 1 degree of freedom because it is not allowed to go up or down because they have to be connected always. For this case, the total degrees of freedom will be 5. What we can see here is that the joints can actually reduce the degrees of freedom of a system. So from degrees of freedom of 6 for 2 unconnected links, when we join them using a full joint, we decrease the degrees of freedom by 2. And when we connect them using a half joint, we decrease the degrees of freedom by 5. You can see here that the adding of a full joint actually decreases the degrees of freedom more than adding a half joint. So now, there are actually a mathematical way to find the degrees of freedom or mobility. In this case, we will apply this in a planar mechanism. So when we say planar mechanism means we are assuming that we have a 2-dimensional mechanism. There are 2 equations that we can use to find the degrees of freedom. We have the Gruebler's equation and then we have the Guttbach modification of the Gruebler's equation. The formula for the Gruebler's equation is given as 3L minus 2J minus 3G. M represents the degree of freedom or mobility. L is the number of links. J is the number of joints. We count half joints as 1/2. And then the G is the number of grounded links. The grounded link is always equals to 1 because there is only 1 ground. For the Guttbach modification, since G is just equals to 1, and since we can separate the joints as half joint or full joint, Guttbach has a different equation, and it is given as 3 multiplied by L minus 1 minus 2J1 minus J2. So M here represents the degree of freedom, L is the number of links, J1 is the number of full joints. Full joints means it has 1 degree of freedom, and then we have half joints, which is the J2, meaning it has 2 degrees of freedom. So the joints has 2 degrees of freedom. So we can use either of the 2 in finding the degrees of freedom or mobility of a mechanism. Say for example, we have here a mechanism. So as you can see, we have multiple joints and multiple links. So our goal is to determine the degrees of freedom or mobility. So meaning we can identify how many possible mobility it can produce. So at first, we need to count the number of links. So the number of links, so if we are going to count, so first the ground is the first link. So that is considered link 1. And then we have this link here, link 2. Then we have link 3, link 4, link 5, link 6. We have link 7. Then we have link 8. So all in all, we have 8 links. So the connection between the slider and this link 7 is another link also. So that's why we have 8 links. And for the number of joint, you can see here we have multiple joints here. So for multiple joints, we count the number of links as the number of links connected minus 1, right? So therefore, the number of links here is actually equal to 2 for this joint. And then we count the rest of the joints. We have 1, 2, 3, plus 2, so that is 5, then 6, 7, 8, 9, and then the connection between the ground here and the sliding joint is considered as a full joint. So because it has a 1 degree of freedom, so it will just either go to the left or to the right. It will not separate from the ground, so that's a full joint. So that is another one. So we have a total of 10 joints. So using the links and the number of joints, we will substitute this value in our formula using the Gruebler's equation. So substituting the number of links and the number of joints and G as 1, then our mobility is 1. Meaning the degree of freedom for this linkage is just equals to 1. So it can only move in a 1 direction. So we can only expect 1 motion for this kind of connection. Another example you can see here. This is also a multiple joints and multiple links linkage. So first, we are going to count the number of links. So the ground is link 1, then we have link 2, link 3, link 4, link 5, and link 6. Therefore, we have 6 links. And then for the number of joints, so the connection between the ground and this link here is actually a half joint because it has 2 degrees of freedom, meaning it can move left or right. It can slide to the left or to the right. This link can slide to the left or to the right. That is 1 degrees of freedom. And it can also separate from that ground. So it can roll, it can move up or down. So that's why it's considered as 2 degrees of freedom. So for 2 degrees of freedom, it's considered as a half joint. So we have a half joint here, so that is 0.5. And then for this part here, since there are 3 links minus 1, so we have 2. So now we are going to count the rest of the joint. So we have 1, 2, 3, 4, 5, then plus 2, so we have 7, then plus 0.5, so we have 7.5. So the number of links is 6 and the number of joint is 7.5. So substituting to our formula, we can see that the mobility here is 0. So this means that it will not move at all. So it will just be steady for this kind of connection. So that is what we meant by degrees of freedom or mobility. So why is it important to know the degrees of freedom or mobility of a mechanism? Because the mobility of the mechanism is the number of degrees of freedom. The degrees of freedom is fundamental in the synthesis and analysis of mechanism. Say for example, in your design process, which we learned in topic number 1, if you have the desired output motion, if you already know that, means in your machine, for example, you already have the desired output motion. If that is known, the number of inputs needed to obtain that desired motion may not be identified or specified yet. So that's why we have to know whether it is the desired output motion can be possible. Cost is the primary consideration here because each required input will need some type of actuator. Say for example, in order to rotate a shaft, we may need a motor or a human operator or a solenoid or a cylinder or other energy conversion device, so that you can achieve the rotation, the translation, or the rolling, that the sliding, the motion, that the input motion that you will need. So there's no requirement that a mechanism should only have 1 degree of freedom so that we can save money. However, it is often desirable for simplicity. Example of mechanisms or machines that has 1 degree of freedom, say for example, it's your lathe, the shaper, or milling machine. Some machines have many degrees of freedom, such as bulldozer or crane, wherein you have a lot of linkages in that kind of machine. So that's why it may require a lot of actuators. So the cost there is expected to be higher than that of a lathe, shaper, or milling machine. A closed mechanism will have no open attachment points or nodes and may have 1 or more degrees of freedom. An open mechanism or more than 1 link will always have more than 1 degree of freedom, thus requiring many actuators. So as it has the degrees of freedom, such as the industrial robots. So now that we understood the degrees of freedom, let us try to use that idea in defining a mechanism and a structure. So in this diagram, we can see the mechanism, structure, and a preloaded structure. This is just a kinematic diagram of each of these differences. So we can see here, if you're going to compute the degrees of freedom for a mechanism, for this 4-bar linkage mechanism, if you're going to substitute the value of the number of links, the number of joints, lower pair joints, full joints, and half joints. So here we are actually using the putback formula. So the modified Gruebler's equation. So the mobility is computed as 1. So if the mobility is greater than 0, or if it is positive, it will be considered as a mechanism, and the link will have relative motion. So meaning the links here will actually have relative motion. Maybe it can rotate or it will oscillate. So this is actually important in mechanical engineering because we want to have motions. So our desire is to have motion. So this is particularly what we call the 4-bar linkage. The second photo, we can see there a structure. If you're going to compute the mobility of that, knowing that the number of link is 3, and then the number of full joint is also 3, then we can get that the degrees of freedom is actually 0. So if the degree of freedom is 0, then we will have a structure, and there is no motion possible if that is a structure. So this is actually important in civil engineering, wherein we ensure the rigidity of, for example, trusses. So that's why the designs is in such a way that you have to ensure that the degree of freedom is 0, so that the trusses or the design is stable. And then for the last photo, we can see there that if we substitute the number of link, which is 2, and then the number of joint, which is also 2, the mobility is -1. So if the mobility is -1, then it is considered a preloaded structure. If it is a preloaded structure, this is actually a redundant structure, meaning the second link is actually not needed anymore because the first link is already enough to achieve what you want to in this kind of situation. So that's the difference between mechanism, structure, and the preloaded structure and their applications as well. So the effect of additional links on mobility can be illustrated in this example. So you can see here a 4-bar linkage. So if you're going to compute the mobility, the number of links is 4, the number of full joint is 4, the number of half joint here is 0. So the mobility is actually 1 if we use the Goodback modification formula. However, if we add link to this 4-bar linkage, as you can see here, we added a diagonal link, we can find that there are actually two double low pair joints. So for this double low pair joints, we can account that in computing for the number of links. So now the number of links is 5. So since we have a double low pair joints, we can count them as another 2 joints in addition to the original 4 joints. So the total full joint now will become 6, and then the number of half joints will still be 0. So the mobility now is equals to 0. So you can see that from a mechanism, it became a structure because the mobility is now 0. And finally, when we add another diagonal link, we can find that the mobility will become -1. So the effect of adding links to mobility is actually to decrease its mobility. So you can see that from having mobility of 1, it became 0, then it became -1. So that means that if you have a mechanism and you want it to become steady, you will just add another link. Or if you want it to become, if you have a preloaded structure and you want to save, for example, parts, then you may remove that part so that you can have a mobility of 0. So now that we understood the difference between mechanism and structure, there are actually instances when the equation that we use in these examples are not applicable. That is what we call the Gruebler Paradoxes. Here, the linkages do not behave as predicted by the Gruebler equation. Say, for example, you have here the E-quintet. So this is an E-quintet because, as you can see in its shape, it's like a letter E. So if you're going to calculate the degree of freedom, so we can actually found out that we have 5 links. So we have 1, 2, 3, and then we have the ground, which is another one, and this one. So we have 5 links. And for the number of full joint, so we have 1, 2, 3, 4, 5, 6. The number of half joint is nothing, so that's 0. So the mobility is, using the Gruebler equation or the Kuhnbach equation, the mobility is 0. So this one obeys the Gruebler equation because, as you can see, this one will not move because of this design. It has a mobility of 0. However, if you design it this way, so this is an E-quintet, wherein in actual, it has actually a mobility of 1. But if you're going to compute using the formula of Gruebler, the mobility is actually 0. So meaning, in theory, the mobility should be 0, but because of its configuration or its geometry, it will actually rotate. So it has a mobility of 1 or degrees of freedom 1. So therefore, the second illustration does not agree with the Gruebler equation due to its unique geometry. So that's what the paradoxes is all about. And we can also find here for this rolling cylinder, the mobility, if we compute it using the Gruebler, is actually 0. But when we have it in actual, this will actually rotate. So that's why it has a degree of freedom of 1. So it also disagrees with the Gruebler equation. So we can find that the paradoxes happens because of how the arrangement of the links or the joints are. So the geometry of the links and the joints is actually very important in determining and predicting the motion. So now let's move forward to intermittent motion. So intermittent motion is a sequence of motions and dwells. An example of this kind of motion is the cam-follower variation on the 4-bar linkage mechanism. So there are many examples of an intermittent motion that is composed of motions and dwells. So this, for example, is a Geneva mechanism. So you can see here, it's actually a series of motion and a series of dwell. So when we say dwell, meaning it does not move, or it just remains as it is. So that is a Geneva mechanism. And then we have here another one, a Rache and Cole mechanism. So we have a series of dwell and motion. And then we also have the linear Geneva mechanism. So each of these is considered as intermittent motion because it is not a continuous motion, but there is a series of motion, stop, motion, and stop. So it's considered as intermittent motion. You can find that in actual application, this kind of mechanism is very much, it's very applicable in practice. So now we are moving forward to the last part of this discussion, which is the inversion. So when we say inversion, you can see here a 4-bar linkage. They have the same links arranged in the same manner. It's just that the way we ground is different. So inversions result from the grounding different links in the chain. So depending on which link you ground, or meaning which link you fix, so that that particular link will not move. There are many possible inversions as the links. However, not all inversions are unique. So some inversions may be the same. A Grashof 4-bar, for example, has 3 distinct inversions, which are the 2 crank rockers. We have the 1 double crank and a double rocker. So in that particular video, we saw the 4 different inversion of this 4-bar linkage. So we have a slider block translates, a slider block which has a complex motion, a slider block rotates, and a slider block which is stationary. The inversion 1 in that particular video is called the slider block translate. So in the slider block translate, this is actually commonly used and seen in piston engine and piston pumps. The inversion 2, which is a slider block which has a complex motion, an example of this is the Whitworth or the crankshaper quick return mechanism, in which the slider block has a complex motion. The inversion 3 is a slider block pure rotation, and the slider 4 is a slider block which is stationary and is used in hand-operated well pump mechanisms. So you can see here that we only have the same links, the same number of links, but they have different inversions. Therefore, they have different applications also. That the inversion again is a result of the grounding. So you can see here that for the inversion 1, the link 1 is ground because of this symbol. And then for this one, the ground is at 2, meaning it is fixed. And then for the third one, the third link is fixed. And then for the fourth one, the slider is actually fixed. So you can see here more examples of inversion, which is also applied in internal combustion engine, in rotary engine, in steam engine, and in farm hand pump. So you can see that by grounding different links, you can actually find different inversion. To know what inversions are, we can simplify the process of identifying the mobility or the behavior of the inversion of a 4-bar linkage using what we call the Grashof condition. So what is a Grashof condition? The Grashof condition is a condition that applies only to 4-bar linkage, meaning we cannot apply this to 5-bar, 6-bar, or other linkages. It predicts the rotation behavior of a 4-bar linkage inversion based only on the length of the link. This kind of condition is independent of the order or interconnectedness of the links, as well as independent of the inversion, whether which link you ground. Say for example, you have 4 links and you label them as the S as the shortest, L as the longest, and the other 2 as P and the Q link. So you have the S, the shortest link, L, the longest link, P and Q, the link that has a length that is in between the shortest and the longest. So we have 4 links because we have 4 bar linkage here. So the condition is that if the Grashof inequality, which is S, the shortest link, plus the length of the longest link, is less than or equal to the sum of the other 2 links, if it is true, then it is considered a Grashof linkage, no matter how they are assembled, because just what we have mentioned earlier, the Grashof condition is independent of the interconnection, the order of the connection, as well as it is independent whichever the link is being grounded. So as long as this condition is met, it is considered a Grashof linkage. If it is false, then it is a non-Grashof linkage. Say for example, for the link that we have, if we add the shortest and the longest link, and we compare this with the other 2 links, P and Q, the sum of the length of P and Q, we can see here that the sum of the link S and L is actually greater than the sum of P and Q, meaning the condition is not met. So it is actually a non-Grashof. So how many unique ways can we connect in order to have different inversions? So if we take 1 link as the ground, leaving only 3 links, and since the ground link can only accept 2 links, 1 on each end or node, you need 2 groups or 2 links. So if we use a combination formula, then we can get a combination of 3, meaning there are 3 unique ways by which you can connect the links. Say for example, you can connect them this way in SPLQ order, or you can connect them as SPQL, or you can connect them as SQPL. The Grashof law states that if the Grashof condition is met, or if the sum of the length of the shortest and the longest link is less than or equal to the sum of the other 2 links, then 1 link will make a complete revolution with respect to the other 3. So there are 4 links all in all. 1 of the link will have a complete revolution with respect to the other 3. Depending on which link is grounded or fixed, you will get 3 possibilities. You can have a crank rocker, wherein if you ground, this happens when you ground either the link adjacent to the fixed link, meaning if you fix the links that is adjacent to the fixed link, if you ground them, then 1 link will have a complete revolution. We can also get a double rack. We may also get a double crank. So a double crank inversion happen if you ground the shortest link. So meaning you fix the shortest link. So this is also called the drag link. So for the drag link, you will have 2 complete revolution. So 2 links will have complete revolution. So for the crank rocker, only 1 link will have complete revolution. Another inversion is the double rocker. So the double rocker happens if you ground the link that is opposite to the shortest link. Say you have the shortest link, and then you ground the link that is opposite the shortest link, then you will get a double rocker. So in this situation, the coupler will make a complete revolution. So take note of the definition of the coupler, the crank, and the rocker in the previous slide, so that you will not be confused of these definitions that we are using here. So some of the application of the crank rocker is when you need an oscillatory output, meaning the output needed is oscillation or oscillatory motion, and then the needed input is a rotary. So from rotary motion, you will produce a oscillatory output. An example of that is the windshield wiper mechanism. So we have the rotation of one link there actually causes the oscillation of the wiper. Another example is the electric shaver. So wherein the oscillatory motion of the blade is actually a result of the rotary input. As well as the sewing machine is also an example of the crank rocker, an application of the crank rocker mechanism. For the double crank, an example of this is when you have your output desired is rotary, and then the input is also rotary. So meaning a rotary motion will also produce a rotary motion. But what happened is that there is a velocity change. So this is applicable in automobile steering mechanism. So in the automobile steering mechanism, we have a rotary input which also produces a rotary output. And for the double rocker, actually this has a very little application. So you can see here in this animation, the inversions of the Grashof 4-bar linkage. So you have the crank rocker inversion, actually has two also types. And then we have the drag link or the double crank inversion, wherein two links rotate when you fix the shortest link. And then you have the double rocker inversion, which is when you fix the link opposite of the shortest link, when you ground it. So we can get the coupler as the one that will rotate. So this one is the crank rocker mechanism. We have the crank which rotate, and then the rocker which oscillate. So we have the crank that rotates and the rocker which oscillates. So that's why it's called the crank rocker. So you can see here, we ground this link here. So the crank rocker again happened when you have this part here, you ground it, and then the adjacent sides are allowed to rotate. And then we have the drag link or the double rocker. So there are two complete revolutions. So each of the link adjacent to the shortest link will rotate. So that's a drag link or a double rocker. And then we have the last one, which is wherein the coupler rotates. So you can see there that our coupler rotates. And the links that is adjacent to the grounded link will not have a complete revolution at all. So those are the the three possibilities when you have a Grashof condition, when you met the Grashof condition. So the inversion now differs whichever link is being grounded. In the case of a non-Grashof case, wherein the sum of the shortest and the longest link is greater than the sum of the other two links, then no link can make a complete revolution with respect to the other. All of the inversions will be double rockers. Application of this kind of inversion is the auto suspension, the auto hood linkage, as well as the folding chairs, an example of this non-Grashof case. So you can see it here in this animation. If you have non-Grashof case, all of the links will actually, none of the links can have a complete revolution. They will just oscillate. And we also have the special Grashof case, which happens when the sum of the shortest link and the longest link is equals to the sum of the other links. In this kind of case, it exhibits what we call the change point. The change point is when all inversions can either be double crank or rank or crank crackers, meaning you cannot predict the motion actually here when you have the change point, because it can either have the double crank or it can have also the crank cracker mechanism or motion. At the change points, the output behavior is indeterminate and the linkage will behave unpredictably, as it may assume either of the two configurations that is mentioned. It can be a double crank or a crank cracker. An example of this kind of condition is the parallelogram linkage, which is applicable in drafting machines, in pantograph, in locomotive drives like trains. For example, they actually use the parallelogram linkage in the wheels. So you can see here in this example, we have a special case Grashof. So we have a parallelogram special case Grashof, which experiences a change point, wherein at every 2 revolutions, it changes its motion. And another one, so you can see that it rotates, then it stops, then it changes again. So that's why we have here the change point. So that happened when we have a special Grashof case. So in summary, the simple inequality S plus L is less than or equal to P plus Q tells a great deal about a 4-bar linkage before it is even assembled. It can tell us whether any link can fully rotate, whether any change point exists, what kind of motions will be possible, whether it is a crank cracker, double crank, or a double rocker. So I hope that the next time that you check your car wiper mechanism, your windshield or wiper mechanism, you will remember this lesson in Grashof as well as motion and machinery.